discuss about the sequence of a control signal. So here, if you're going to consider about this particular diagram, while considering the sequence of control signals, each step in this sequence is going to be completed in one clock period. Yeah, a counter may be used over there to keep track the steps as shown in this figure. So each state or count of this counter corresponds to one control step. Here, the control signals are going to be determined with the required symbol or required input from the content of the step counter, as well as the content of the instruction register and the content of the condition codes flags, and the external inputs such as MFC signal or interrupt request from the external devices. So all this four inputs are going to be, all the four input parameters are going to be required to determine the instruction, which is going to be control signal, which is going to be produced from the coder and decoder. To gain the insight to the structure of this control unit, we start with a simplified view of this hardware, which is involved the decoder encoder block diagram. With this decoder and block diagram, which is a combinational circuit that generates the required control outputs depending upon the state of all the inputs as conditional codes, external inputs, control step counter input, and the IR input. By separating the decoding and encoding functions, we can obtain more detail about the block diagram. Let's discuss about the separate diagram which have been given over there. A block diagram, a separation of the coding and encoding functions. Here, the step decoder provides a separate signal for each of the step from the different time slots in the control sequence. Similarly, the output of the instruction register decoder, which is going to be given to the instruction decoder, which consisting of separate lines for each machine instruction as INS, which varies from INS1 to INSM, difference upon the line. For any instruction which is going to be loaded in the instruction register, one of the output line INS1 or INS2 or INSM is going to be set to 1 and other lines are going to be set to 0. Such a way the input is going to be processed to the encoder function, and this encoder function, which is going to be again depends upon the inputs of conditional codes, external inputs, step decoder, and the instruction decoder. Depends upon all these four inputs, the encoder which is going to produce the output. Let us see how it's going to be generating the signal for the Z-in, or it may be for the end. So in general, if you're going to discuss about this particular, the hardware control can be viewed as a state machine that changes from one state to another in every clock cycle. So depending upon the content of the instruction register, the condition codes, and the external inputs, the output of the state machines are the control signals. The sequence of operations which are going to be carried out by this machine is determined by wiring of the logic element. Hence, the name is going to be called as hardwired. So a controller that uses this approach can operate at high speed. However, it has a little flexibility and complexity of this instruction such it as an implemented in a limited way. Let's discuss about the generation of the signal Z-in. So if you're going to see about this particular diagram which I've shown here, which consisting of an AND gate and an OR gate. So if you're going to see about Z-in is equal to T1 plus T6 into add plus T4 into BR branching instruction plus etc. It's going to be there. So here the input signal to the encoder block is going to be or combined to generate the individual control signals Y-in, PC out, add, end, and so on. An example of how the encoder generates the Z-in control signals for the processing organization has been explained over there. The circuit is going to get implemented with the AND gate and OR gate. So let's consider about this input. So here the T6 into add is going to be the instruction and T4 into branch instruction. So I'm going to do this one. T6 add will be given to an AND gate and branch into T4 is going to be given to a another AND gate, and outcome of this two AND gates and along with this T1 input, which is going to be combined to a OR gate, which is going to produce a outcome as Zin. This is going to be the generation of the Zin input control signal from this particular diagram. Such a way we're going to generate the signal is going to be asserted during this slot T1 for all instructions during T6 for an add instruction, during T4 for an unconditional branching instruction, and so on. Such a way the logical functions for Zin is going to be derived from the control sequence from this particular equation with the help of this logical circuit. Let's discuss about generating end signal. So in this generating end signal, it's another example, the circuit that generates the end control signal from the logic function end is equal to T7.add plus T5 dot branching instruction, unconditional branching instruction, plus T5.n bar, T5.n plus T4.n bar into branching, conditional branching instruction, etc. Here conditional branching is nothing but when branch is going to be greater than 0, that is a condition, n and n bar. N into T5 with conditional branching will be given to one AND gate, n bar into T4 into conditional branching will be given to one more AND gate. Whereas T5 into BR, which is going to be taken in another AND gate, and first input T7.add as given to another AND gate. So all the outcome of this is going to be get additive because we are going to have an add symbol in between this additive. So all are going to be get added over there through the OR gate. So individual AND operation with OR operation is going to be present to us. Such a way the output is going to be producing an end signal which consisting of T7 into T7 and add plus T5 and add and branch instruction plus T4 and n branch instruction plus branch dot T5. Such a way it's going to doing its operation, and the end signal starts a new instruction fetch cycle by resetting the control step counter to its starting value. Hence what happened, if you're going to see about this figure, so the another control signal run is going to be present over there. When set to 1, run causes the counter to be incremented by 1 at the end of every clock cycle, and when run is equal to 0, the counter stop counting. This is needed whenever the wait memory function control signal is going to be issued to cause the processor to wait for the reply from the memory. Such a way it's going to do its operation. Once the end is going to be present, it's going to restart the counter and the process is going to be waiting for the next instruction to be executed, or next control signal is going to be get generated after the clock is going to be get inserted. Such a way it's going to do its operation. So this is the detailed description about the block description of an hardwired control unit. So moving on to the topic, a complete processor. So here this block diagram which is going to specify with a complete processor, the processor consisting of an bus interface, a cache memory, one is for the instruction and one more is for the data, and it consists of an instruction unit, integer unit and floating point unit. So the processor and the main memory and input output peripheral devices are going to be connected through a common system bus. It's going to be connected through a common system bus. So whenever the memory is going to be connecting towards the processor through a system bus, if any instruction is going to get transferred or data is going to get transferred over there, the bus interface is going to be connected over there. Through this bus interface, the instructions are going to be fetched over this way, whereas the data are going to be fetched from this way, and depends upon the data whether it's going to be integer or a floating point data which is going to be get fetched in this particular unit. Such a way the processor is going to do its operation in a complete way.